Hello.
Hi, sir.
Yeah, hello.
Yes.
Yes. So, do you have any doubts?
No, no, nothing currently as of now. I just joined so that something you'll discuss or other students will ask doubts or like that.
Okay. Hello. Hello, Naval. Do you have any doubt?
Sir, good evening, sir.
Yeah. Good evening. Do you have any doubt?
Um, um, in week 4, yes, sir, but I'll wait because last time it stretched a bit, so I'll wait till everything is over and then I will complete so that I don't interrupt your flow, to be honest.
Okay. Um.
If I can ask now, I can just put the as practice assignment question where I'm not able to understand the concept.
Yeah. Go ahead.
Okay, okay, sir. Okay. Um, Sir, in the practice assignment 4, the fourth question, professor mentioned in the one of the lectures that they remove the W naught term because it adds to bias and it centers where the W naught is coming from, and that's the reason they avoid bringing W naught in the gradient descent function or instead of nag or others part. But in question 4, it asks the impact of W0 on history at 100 iteration. I couldn't understand like how will grad W naught impact uh, uh, UT. Question 4.
You want week 4 question for practice assignment, right?
Sir, yes, sir. Correct.
Um.
The impact of W naught or grad W naught on the 100th iteration, like
Okay. So here, um, right. So consider a momentum-based gradient descent. Okay. This is the rule. Suppose runs for this. What is the contribution of do not to history? Um. If your answer is mm, mm, okay, so this is very straightforward question. So what you have to do is uh, so let's say at first when we compute the gradient first time, right? W0 it will contribute fully like 100%, right? Uh,
yes, sir.
100%. The next time it will contribute so whatever is beta here, right? That much amount. So if you see this formula, if you expand the formula of this gradient, right, then you'll get like 1, then multiplied by 0.9, then again multiplied by
Beta
0.9.
to the power beta zero point 0.9 to the power 99 into something. That
Yes, yes, yes.
yeah, but because the professor mentioned that they don't use W naught to avoid the bias of anyway. So I'll maybe that's the right answer. They say that they do not start with W naught because it sets the impact of where we are starting from, and then that impacts the approach towards the error function, how it approaches the valley. So they do not set a W naught. They just they just calculate it directly from. Understood? Maybe yes.
No, nothing like that we do. I don't
Okay.
think that's being told in any session. Or any sir has told that.
Uh, yeah,
We
I'll bring out that maybe video point and I'll put it in the Discord. I'll not take too much time. That's the reason I was getting confused that the professor somewhere mentioned that it does not depend on W naught. It's independent of W naught and we don't care. So that's the reason I was a bit skeptical, to be honest with you.
mm, I think he means that the dependence of initial gradients will as time goes on it will reduce. That is the idea behind this weighted moving average. So this is what weighted moving average does. That initial values are there will impact very less when we are at the end of this time, right? So loop. So as you move in the loop, the impact will reduce. That is the idea. So initial will impact less now, or maybe it will not impact at all. You can think like that, but like that only. So it will multiply by 0.9, 0.9 and all, right? So power 99, as you said. So
Yes, sir. Yes,
yeah,
sir.
so that is there. Like uh,
Yes, sir.
it's not like it will. Um, he wouldn't have said it like that.
Yeah, yeah.
What you are saying,
Maybe
maybe.
there is misunderstanding. I'll check if I find that somewhere there. I'll put that link directly to that timestamp so that maybe people can, maybe you can. Put it on the Discord later. So just one small question about again on the week four, sir. That this is during when the professor talked about the adaptive gradient descent and then the NAG part there. So there, the stochastic versus batch. So there, professor mentioned that they are using suppose a batch of 10 and n by something, n by 8 or n by 10, and then
Yes.
after every 8 or 10, they take a sample and they throw away the previous one and take the sixth, and then they move ahead and then they do again. So that stochastic, to be honest, I could not understand. If you can spend maybe 2-3 minutes just to, yeah, this part, because what does it mean to take, because unless the weights are in an ascending order, if the weights are completely random, then suppose I take a random number between 1 to 100, between 1 to 100, and they are not in ascending order, and from first number could be 79, other number could be 3, other number could be suppose 98. So then if they are not in a sorted way, the and you throw away the remaining part and you only take sampling after every x numbers, then you will never converge. You will just keep on oscillating depending on the probability of what you are getting at the x n by bth sample. That's what was confusing me. That random sampling on a non-ordered set will not lead to a convergence. Maybe you can explain.
So I'm not sure about what Sir said about, like, I don't exactly remember this, but okay, let me explain what is stochastic to you. So what we do in stochastic gradient descent is we have, let's say, 100 data points. Okay, so after each data point we update the weights. After each data point I update the weights. So that's what we did in back propagation also. So the example shown to you by Sir also, and we also did in last session, the back propagation algorithm, which we as of now understand is stochastic gradient descent only. That one data point goes in, it could be of any size. Okay, so x could be of r of d dimension, right? So that will go, it
So
will.
so this is sorry for interrupting. So suppose this data points where I'm confusing between layers, and suppose there are 4 layers and each layer has 10 neurons. That is 40 data points, or
No, no,
40
no,
data
no.
point and neuron. And
One data point is data, whatever the input is, right? The what we get as a
the x. So you're saying x. This is like
x, yes,
that will
x is
transpose x plus b. So that x, the number of elements in the vector x is the number of data points. So we are
yes,
not
yes.
talking about the number of neurons and number of layers.
No, 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 nothing
Okay.
like.
How big is the input data to a
Yes,
training network? We have training data or a validation data which is fed to network. So yes,
yes, yes.
yes. Please continue.
Rows and column. So if you have rows and column idea, one row is the data point. Okay, that
Okay, sir.
one row will give, like machine learning, one row one data, second row another data point, uh, right? So one point by point you can think. So maybe if you plot this in this hyper geometric, right, then it will become point, right? So in this big
Yes, sir.
space,
Yes, sir.
hyperplane. So that's what point, that's from the point comes from. So one point is there. So one point, each point is called like stochastic gradient descent. So basically you take one point, you go through the forward pass, you compute loss, you and then do the gradient calculation, and then do back propagation, right? So that the one cycle completes at one using one data point only is stochastic gradient descent. Then you take second point, you do the complete cycle. then you take third point and you do the complete cycle. That is what stochastic gradient descent do. So vanilla or this batch gradient descent means you take, let's say one data point goes in forward pass, okay, then second will also do forward pass, third will do forward pass, fourth, fifth, till whatever data points you have, let's say 100, then 100 forward passes. Then you accumulate all the losses, okay, you sum all the losses, individual losses, you sum them, then you take the gradient uh, of it, like, right, so you do back propagation, so you take gradient and then do the back propagation. So one cycle will update, so all the data points will be passed and one update will happen to the weight. But in other case, like stochastic, as many data points are there, that many times the weights will update, right, because that's how the method works. But if you can choose a midway also, that I don't want to give all the data points, I don't want to give one also, I wanted to generalize it better, so give some amount, right, so 50, 100, 200, you can choose depending on your use case, right. So that part, if you choose, then that is called mini batch. So mini batch you can decide and give, right. So that's what it is, mini batch gradient design. I think this is all. I think this is being covered in MLT as well. So same
Yes,
thing.
sir.
If
Yes.
you understand MLT, then this is same as that. Nothing new. Okay, maybe it's
Yes.
being taught by different professor, but the like fundamentals are very same.
So my only confusion was coming was, so suppose if we take mini batch gradient descent, and then because then the value or the dimensions of x, the first row of vector or matrix x is suppose having, say we have suppose a matrix of 6 by 6 matrix. So first row has 6 elements. We take a batch of 3, so it will have 3 and then second batch of 3 again. But our W transpose, our W vector is suppose prepared for a 6 by 6. So W transpose X will be invalid. If we, so do we change the W when we use batch gradient, and we again change the W when you use the full one? Because then the vector multiplication will throw an error if we reduce the number of dimension of X.
No, it will not throw an error. Uh, the reason is, okay, so mathematically, okay, let me show you. Uh,
So you got the idea, right, sir? What I'm trying to
I got it, but it will not throw an error. I'll see. I think you are thinking little different on that, but um, okay. So yeah, Lakshmi.
Yeah, I have a general question. So in week four, many optimization techniques are mentioned, like nest drop and moment based. So my question is, they will converge to local minima or global minima? Means- Hello.
I think sir is on mute.
Am I audible?
Yeah, you were audible, Lakshmi, but I think sir is reading the screen is on mute.
Hey, yeah, hello. Yeah, sorry.
Yes, sir. Yes, sir. You're audible.
So, okay, so in all the optimization or whatever you do, you only can surely say that it is a local minima, because generally we don't know what is global minima in the loss function. If they are convex functions, then you can expect that, okay, it will converge to one or global minima, right? So if multiple minimas exist, then you don't know actually which is a global minima, uh, because what we know in reality is we know only one point in the whole space of a loss function, right, at a point where weights are given to us, weights, and from that we can compute loss.
Okay, so if a function has say five minima in which one is global minima, so is there any technique I will reach to global minima in deep learning?
No, not possible.
Okay, thank you.
Okay. Okay, so let's say your x, you are now saying that matrix or the vectors will not multiply correctly, right? So let's say my data point is there. So
Yes.
let's say this is my data point. Okay, one data point. Then this is my another data point. So I'm doing this brackets to make it discretion, but you know that you can directly write it as a matrix, and it's the same thing. Okay, so let's say just take something like this. Okay, so 3 points are there. I have taken as a mini batch. Okay, so this is like, you can say, mini batch of size 3. Okay, so this is my x. Now let's say your first this is my first network. Okay, which is, just take, let's say, two neurons are there. Okay, so how this is my input. Okay, I'll draw input as a blue. So this is my input uh, layer. This is my hidden layer. So okay, so this is my hidden, which has two neurons. I can decide how many neurons I want in my hidden. Okay, so which I did. Now it will do this thing, right? That's what we'll do. So let's say what will be the weight expectation I have, like, or what will be the weight matrix of this is. So I'll call this as W1, or this as W1. So weights associated between input and the first hidden. So I'll expect that first neuron will get 3 something, right? So 1 1 1 1 1 2 1 1 3. Okay. Now 1 2 1 1 2 2 1 2 3. So this 6 weights will be there. Correct. Now what I have to do is, I have to get a z and then apply sigmoid over it, right? So z, and then I'll apply sigmoid over z, right? Something like that I'll do. So as of now, you can consider z as wx plus b, right? We kind of understood that why we are not taking transpose as of now, because we already did here. Like, you can think that this is the transformed form of w only. Okay, so now let's say if I do this, this is, so this is how many, 2 rows and 3 columns. Now the weight, whatever you are getting is, or this x you are getting is, how many rows are there? 3, right? And it could be anything. So as of now, I've taken 3 as a batch size, but let's say n. Okay, n or any number you can wish here. What is in the slide? Okay, b. Okay, so batch size. Just consider this is a batch size. So you will get an output of 2 cross b. Is it okay?
Yes, sir.
So you will get the matrix multiplier. There is no issue with it, right?
Understood. Yes, sir.
Now you can apply sigmoid over it.
Yeah.
So just you have to remember one thing, that the output you are getting for each point is 1 column. So this first column of this 2b is the output of my. If you would have passed, let's say, one data point, then what you would have gotten? Like, you would have gotten one column, right? And then second point you pass, so you got another column. So this is for second point, this is for third point, and so on. It got contributed, and then finally you had b such column, so 2 cross b, and each has 2 values, right? So 1 and 2, and so on. So now you have to kind of think in that way and then do the multiplication. So it will not have any issues with multiplication or the dimensions are okay with the function. Something you have to do with respect to back propagation and all, to ensure that the loop is working correctly. Okay, otherwise it will not throw an error.
Yes, understood, sir. So the number of batches we take is based on, so we don't need to know the number of neurons that are there in the entry network to select the number of batches. Like n by b should be a number which is a multiple of number, because we don't know how many neurons are there in the entry, because all, like the machine learning models out there in the world, will not tell how many neurons are there in the entry level. So we cannot, but we know, suppose, what is the data we are putting in, but we don't need to care about whether we are matching with the number of neurons in the entry layer. That's
No. See, what I said is, say, this is input layer. So you should know at least input size, right? Input size you would know, right? Something.
Yes, input size we know. Yeah.
So this, from that I made this. Now this is my hidden layer. On hidden layer, I can actually choose that how many neurons I want. So this is of my choice. So it's not like I don't know. I know it because I have to choose it. Right. So whoever created this, they have chosen it. That this
Understood.
many neurons I want. Generally, they prefer 64 or 128, something like that. You know that 2 power something they'll choose.
Yes,
That
yes.
is like more preferred way to select neurons. Okay. But they will choose it. So here I have choose 2 as my choice to explain you. You could take anything. So that's how first hidden layer. Then you could have another hidden layer with 4 neurons, right? Something like that. You can do as whatever you like. Okay. So this is my second hidden. Then it will this 2 cross B will go there inside this 2 cross B size matrix will go there, right? Then it will be so W2 will be it should have 4 rows and
I think W2 will be H1, right? Because H1 is the input to W2. No? So because H1 is W transpose X plus B is the output, then we put G of A. So A is W transpose X plus B, G of A is H, then H becomes the input to the next one. So H
yes, sir.
becomes
So this
W.
will be A1. This is then H1 you'll get, then A2 and H2, right? So
So H1 is same as W2.
you can take this as A1. Okay, A1.
Yes.
So as of now, W1 X plus B.
Yeah.
Then you'll get whatever.
Then
from,
we'll take a G of A1 is equal to H1. So then you apply the function
something like this.
sigma on A1 to get H1.
Yeah.
H1 is G of A1. That's what was taught. Then H1, the number of H, the value of H1 becomes W2. H1 is same as W2, I guess.
H1 is same as W2.
Yeah.
No, see, W's are weights, right? H1 is, I mean, in what term you are saying same?
So the moment we have H1, then just like we do W transpose X plus B, next time we will do W2 transpose H plus B. X becomes H.
Yeah, yes. So whatever inputs is yeah. So this
the
H1
dimension
or
should match.
correct. So this will become your
Input to the next. H
input.
is the input to the second layer of
Yes. H,
and then the
that
dimension
becomes
matching will
input.
happen. So
Yes.
mini batch gradient. So if we do, there will be no matrix multiplication error coming. Understood, sir. Understood the concept.
Yeah. It will
Yes.
not have any error.
Yes.
Okay.
And sir, one before you start the part, the one that was Betamax part, when sir showed that T by 250 and then 1 minus T by 250, and then he said that you can select between 0.9, 0.999 and then 0.95 and that part. So my general understanding here is, suppose if we take A is equal to W transpose X plus B. So first we try to optimize W. This is again, I think, in the the last one, the line. Yes, sir.
I think I understood.
Yes.
Was
T by 150.
I think this one.
Yes, sir. So
Okay.
So because at present we are trying to optimize eta and then beta, and so because eta is the weight, how do we update weight? So are we trying to optimize W transpose or W by changing beta here? How does W and beta come? That's where I was a bit confused. The weight update.
See,
Yes,
this beta is momentum term, right? That how much momentum you want. So earlier, so this beta is coming from the momentum part, right? Not from this. So see, as of now, what we are doing, say before that, just before, because here's a context changes. Before that, we are going into learning rate, how to reduce learning rate. So see, the essence of week 4 is, so first we try to look at that how we can improvise a better gradients. Okay, so that is the idea. So okay, okay, let's draw. So before that, so this is momentum based, right?
yes.
So just think about this part, that we have 3 things in this, right? WT and some learning rate, and then this is gradient. So this is gradient part, this is learning rate part. I can't control this part, right? I have no control over it. So there's nothing I'll do on that. Now I have something I can do with learning rate or gradient. So two things. So now researchers will think, okay, is there any better way to do something on learning rates? And then this annealing the learning rate comes into picture, that they will do annealing the learning rate. Now, is there anything better I can do with the gradients? So then this optimizers come into picture. So this leads to optimizers, and this leads to annealing the gradients and all. Now in annealing the gradients, they come across something called this momentum part, right? So this beta and all comes into, which is beta, right? So this part has another like two three components, right? So
Understood,
they
sir.
went
Yeah.
into how
Yeah.
we can maybe do something better with beta also. Okay, and maybe if something they can do with, so I think gradient they can do anything, that's what they will get. Maybe they will do something with ut minus 1 as well, correct? Like how ut minus 1 is being designed.
So
Currently it is like just we are taking it, then we'll change it to something else. So next optimizer, like week 5, few more kind of optimizers will come, where
mm,
you will see that ut minus 1 is also changed into something, right? So this is all researchers do. They
trying
had this
to
many
optimize.
components and they do something on it. Okay.
Yeah. So, because when we understood very from the very fundamental concept, A is equal to W transpose X plus B. That's the most fundamental equation that we can start the course with. So
Yes.
there, when we and then when we see the formula above, when they try to update W and then we try to put beta and then try to see that the impact of all the depending parameters. So because in our examples in week 3, we were given as students, we were given by IIT the W1, W2, W3. We simply multiplied and we did the computation and we solved the assignments. So are you saying that in real world, W2, W3 are not given? People have to get W2 also, W1, they're not even given W0. What in real world, how do they get W0? Uh,
So okay,
yeah.
so what they do is they say initialize it to some random number. So W0 initialize random numbers. Okay.
Oh,
This,
understood, understood. So in maths, there's a concept of Newton-Raphson method where there is a radius of convergence and everything converges. Is it something like that when everything should converge if the formula is such that random numbers is within the radius of convergence, it will always converge in a finite number of ways to a finite solution. Is it something related to that? We
uh,
learned that in English.
I am
No,
not sure
no, no
about that.
worries, no worries. Please continue. Sorry for interrupting.
Yeah. Or so I think we don't have in our course, but there are certain ways to initialize weights also. So one is called random number. There is another which is a he initialization. So this he is, I think, name of maybe one or two researchers. They do it. So he initialization. Then there is something they do. Another is Xavier initialization, something like that. So this Xavier is also another maybe research or something, but these are the names of initialization. That way they initialize the weights. But as of now, you can think that they are randomly initialized,
Yeah,
and
understood.
then we optimize it. Okay,
Yeah,
so
because
using backpropagation.
yeah, because if you remember in the last class we talked about how cleverly of and for convenience the loss function was chosen to be log, so that if you
Hmm.
take a derivative it will become 1 by x. It is not put in the way so that it will diverge. It is always 1 by x, 1 by x square, 2 by x cube, 3 by x 4. It's chosen in the way so they have already kind of manipulated the log function. Then we also manipulated the sigmoid function. We have ensured that there is no diverging. If I take a million transactions or million derivatives or million functions of sigmoid, it should not diverge. That's the first part. That means the program should not have a runaway effect. So they have taken the care of log function. Then they took care of the sigmoid function. Now they are taking care of the W because the W transpose X. X we are not under control. Bias maybe we can control that what would be the excitation, what would be the suppose not excitation part there. In W transpose X plus B, now we have moved first the sigmoid, the g of x, the sigmoid function we have control. Now we're trying to the only factor that we haven't controlled till week 3 was W. So we went into W, how we can control W. And then we went into W minus eta. So then I think then that's where what you said 5 minutes ago becomes sense. Then within W they went even further inside. They said eta and W ut. Then they go into eta, how we can optimize eta, then ut, how we can optimize ut. They're trying to optimize element by element so that the overall output is optimized further and further. Is that the fair way to understand the entire deep learning?
Yes, yes, correct. So that's what we'll do. See, this is the basic structure which we covered in the week 3. That is a basic structure. Now there is optimization will come. Then something they will do with, okay, so now weights are there, so they will do normalization, batch normalization, something like that will come. And so several things, right? So wherever the multiplication addition will happening, the thing is it happening the best way? Is there anything we can do with the mathematics we know as of now? So they will try to manipulate things, and then they experiment it, and they'll realize if results are coming better, then they release it as a research paper. Then all the researchers or all the users of deep learning across the world try to implement it. So that's how
Yeah.
the community grows.
So I guess that's where the hyperparametric tuning and optimization comes. You take sigmoid, you take tan h, you take logit, you take all the functions. So you try to play around everything. You take log function in the loss, you take hype sigmoid tan h in that part. You change w, you change b, excitation versus some inhibition. So everything except x. So that we get to the once we get to the output, the next part is how to get to the output faster. So when
Yeah.
we play around, that's exactly what we're trying to do, is trying to figure out what we do in programming with hyperparametric optimization, where we play around with a vast number of permutation combination just to figure out what suits. Is there a universal truth that suits everything, or does it depend on X in the end? That on the type of data. Suppose I'm trying to ingest image and trying to predict skin cancer. Suppose I'm trying to ingest an email trying to predict spam or not spam. Will the choice of that hyperparameter be independent of X, because we're not playing where we are keeping X out of the picture? We're doing everything except X. So
Mhm.
does X matter or does X not matter? Only everything else except X matter. Sorry if it's that's the final question I had, to be honest, because I could see where we are going, but we are keeping everything independent of X. So
Mhm.
does X matter?
No, so I think X does matter, because that's what see, if X didn't matter, then we could have formed a model, right? A model which could have worked on all the world problems, right? But it's not working
I think that's
currently.
where the AGI is about. It doesn't care whether you're trying to understand, ask a question, or whether you're trying to upload an image and try to identify whether the cat or not cat. That's where, when X doesn't matter, that's when it becomes AGI, I guess. Is that a fair assumption?
Yes, it could be. I'm not uh, well informed about AGI, so I can't say it,
Yes,
but it
understood.
could.
Sorry for the diversion. Understood. Thank you, sir.
Yeah.
But,
Okay.
but what the part where we take the T by 250 and then we try to optimize it, and then we take the maximum 0.999, that's the maximum, and then we slowly try to select that part. That's where my doubt was. But
Yes.
understood, it's all about trying to update ETA or UT. This week is about ETA and UT and how to make uh, uh, very valued or thought about changes to ETA and UT. And there should be some
Yes.
reasoning behind, not random ETA and UT, because we can like take a random number for ETA and UT and try to play around and see till the end of the world what will happen. We try to find out some mathematical way to structured way to figure out it. And please, if you
Yes.
can summarize this one, that would be answer to my question. How does this help?
So, so what happens is, you can start with, let's say, 0.999, okay, beta, and what it does is so this beta will get multiplied with the uh, previous gradients, right? Let's say w t minus 1 or ut minus 1, okay, ut minus 1, and then I'll take gradient or something like that, right? W t. So this whatever this beta is going to get multiplied with my previous gradients. Now, do you want to take consideration of previous gradient low or high? That is being decided by this beta parameter, right? So the idea behind this is that initially, let's take a lesser or mm, so if I have, let's say, 0.67 value, that means I'm taking less consideration of my previous thing, history, right? I'm not taking too much consideration of history, and that is true because I don't have much history accumulated also. So I can't rely too much on history as of now when I start. Then as it will grow, it will start taking more consideration to history, right? That's what beta is a formula. Beta UTR. That's what. Okay. Okay. Yeah. So so when you will start with this, so let's just take that t is 0, right? That initially t is 0. Then what will be the value of this beta t or beta 0 in that case? So I'll take minimum of this thing, right? 1 minus. So now I have 2 power minus 1. So log 2 base. Now if I take t as 0, then this whole term will become 0. And log of it will become, so this will become log 2 base 1. And anything 1, so log 2 base of or any base 1 is 0, right? So this value is 0. And so let's say this whole term will go away, and I have 2 minus 1 or 1 by 2. So I start with 0.5. Okay, as of now I take minimum of both, and I can say that initially let's say this much history you should consider 0.5. So as you will increase, so let's say you go till 250. Now it makes sense to compute for 250 for ease of calculation. Then you will see that the values will now beta will change, or it will increase. So it will go till whatever beta max you choose, it will go there, then it will get constant. So then after that beta max will only being used, you can consider like that. So at 250 what happens is you get this as 1. Okay, 1 plus 1 is 2. So log 2 base 2 is 1, right? So what you get is 2 power minus 1 minus 1, or basically 2 power minus 2. And that you can write as 1 minus 1 by 4. Okay. So if you reduce 1 by 4 from that, it will be 0.75, right? And this was, let's say, 0.999, and you take minimum of that, you will get 0.75. So you see it increased. Again, you can take it maybe at 250 into 2, as of, like, consider, like, let's say 500, right? So t beta equal to 500 you can do, and you'll get some value. So it will increase, and finally it will reach at 0.9, or it will go above that. And that's where this minimum value will become this. So you don't want to go above 0.999. And that is the idea, that initially don't rely too much on history, but as you go or as you move too much, like as you move in the gradients, like in the path, then you can take consideration of history a little bit more, right?
Yes.
So because initially it is finding the direction, it could be, let's say, this anything, but once, let's say, path is being decided little bit, it can, you can have more confidence over it. That's what this guy is saying, skewer.
Yes, understood. That's how I guess the values will change, and I think then the moment we have W, suppose one value of W, so it interacts with whatever value of X is, and then those biases. Then the H2, the next output at the end of first hidden layer of neuron, will again update W based on H2, or will W2 will not be dependent on H2. It doesn't depend. So yeah, because H2 is the input, so it's independent of H2. It just, so the point I'm trying to say is that if the divergence in H2 or the improvement in H2 over H1, and is it converging, the is the value of X, H1, H2 till the Hn or the final Y output? That's where because Y is dependent on X, which is the input here. So
Yeah.
Error term is Y minus Y hat, and Y hat is dependent on the entire X and H in the part. So if W improvement is W is linked to W minus eta ut1, and eta ut1 is dependent on beta, and nowhere we are calculating H1 minus H2, which is the gap, which is the improvement post one more layer of neuron. How do we know that that layer helped?
Okay. So I think you missed a major point here. That point is this part. So if you see the code given to you, that would make much sense. So Okay. So okay, let me write it out. That would be easy for me. So what we are supposed to do is we have some weights, right? Let's say W0 or it's a timestamp 0 or initialized weight. Okay, this I have. Now what I want to do is whatever my weights are currently, I want to optimize it, or I want to change them in such a way that now my loss should decrease, right? So whatever gradients I'll get with respect to W's, this I will use to optimize or to reduce or to change the weights. Now weights will be changed. Okay, this W1. Sorry. Okay, so W naught minus this. So this was initialized weight, and then I get some another weights, right? Now what we are doing is we are, instead of directly using this del WL, we are saying that instead of doing that, can you do something like UT or something, U0 or something, and then they are saying okay, U0 is something like I'll take beta of my like previous one, let's say -1. Okay, so basically you understand T -1 when you go across, then plus whatever gradients of current this are there, right? So W del WL, right, like this. Okay, so now I'll use this as of instead of using the thing. Now, so whenever I do this, I update the weights. Now what will I do after updation of weight? I'll do forward pass, right? That is the idea, that I do forward pass. After every weight updation, I do forward pass, then I do backward pass. So forward pass and backward pass. So the cycle is continuously going on. Now, so again, when I reach here, the weights are updated. How weights are updated? Using this formula. So this whatever optimization you use, anything you use, and then on base of this, weights will be updated. Then using new weights, my forward pass will happen, and my again new loss will computed, right? And then loss will leads to back propagation. And using this, I'll do the back propagation.
Understood. So that's where the L part helps in terms of the loss function, because the loss will come down. So again, the U naught will keep on getting smaller. So those updates will keep on getting smaller. So then it links back to WL.
Yes. So this in forward, this H will come. All the H's, H, A, everything will be there, right? After doing the weight updation. So as of now, they showed. So here this W1 is timestamp. Okay, just in case this is T equal to 1. So we'll do for all the W. So initially or when we understood things, we said that this is W1, 2, 3 are the matrices. Okay. But now what we are saying is W1 is timestamp. Like, so you can think like W1 computed as T equal to 1. Okay, that's what this means. And
Understood. Now it makes sense. Understood. Yeah. Understood.
okay,
That
so
was the biggest confusion.
yeah, then I have to update W1, which was from T equal to 0, and then from that, I have to subtract this learning rate time, or you can take gradient of this. Okay, gradient of W. So here I'll use W1. Okay, this is the matrix one. I'm saying L. That's what I have to do.
So in one forward pass, if we come back, so like in the week 3, we saw that we only go one direction. We go toward H1, H2, S3, and we finally get something. Here we are doing coming back to again layer 1, changing the value of W1, T is equal to 1 or T is equal to 2 again. Then we are again going back to a loss function, which is the output layer. And then we are again coming back and again updating W2. We
Yes.
keep on doing this till we
Reach the epoch. So we have epochs, right? Epochs
Yes.
equal to, let's say, 1000. So you'll do for 1000 epochs.
But the number
And
of computation will increase.
Yes, we have to do that, right? So that's what these epochs are. So in ML, you would have done epochs, right? See,
Yes,
what
yes.
I'm doing for I in range of max epochs. So max epochs I have decided. So I'll do this many times, right? So here I think what is max epoch? Not given, but you can take something 100,000, right? So that's what it'll do continuously.
Understood. So we are just trying to reduce the time taken to reach to minima, but we are increasing the number. So if it takes 1,000 computation to reach to minima, it was doing 10 computation and taking 100 seconds. We are doing 100 computation and taking 10 seconds. The number of computations remains the same, but the time taken reduces to reach the minimum. Number of iterations to reach the minima reduces, but the number of computation
I
benefit is faster conversion. Because the
I
computation is
don't.
rising. In a previous one, there was only one computation done. Now again, you're coming back. The same way we go to W2. Again, you'll update W2. You keep on doing
Yes.
forward, backward, forward, backward. That was not there in
Yes.
3. The number of computation is increasing for what? We are getting faster convergence. So we have to
No.
do something to
No.
get.
No. No.
No,
No. 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 No.
at least sorry.
The computation, yes, faster convergence, but the computations, why we have to do epochs is, so let's say I have this as my loss function, something. This is for understanding purpose, okay? That I have this kind of loss error surface, right? So this is what called error surface or loss function, that something like that, right? So I want to converge here. So this is my minima point, okay?
Yeah.
Local minima you can take. Now how will I do? If my current loss is here, I can move in certain direction like this. Now what I can do is I can take huge steps, but that I'm not going to do. The reason is I might not actually converge here. I might, let's say, shoot up. Okay, so that is the drawback of this. So I should only learn in like small steps. That is what learning rate is. So small step I do, right? The small step. So one step. How am I doing this one step? This one step so is using this update rule. Okay, so update rule will give me new w's. So using w's, so let's say this is my loss compared using w, right? So you can take w as x and loss as y, and that's how you got this function. Now as some w's are there, you will have this loss, you want to reduce it, so w's will change and then give you another loss, another again w's will change and give you another loss. So finally you will reach here. So this is what minima is. So you have to do the computation. uh, the reason we are doing epochs is because we wanted to do this gradient descent. So this gradient descent is the reason of this epochs. Okay, computation and all will increase, but that is not the reason or anything we are trying to save or anything. The reason of that is this
Yeah.
algorithm works that way.
Yeah, because Professor mentioned, and then he gave the example of Velocity Gate and the Phoenix Mall and whatever. And then also he showed in that the time taken to converge is easier. And then he said that after X number of iteration, so he took iteration or time, which are both synonyms of each other. And he said that it's converging faster. But if I
Yes.
suppose I say I make someone do 1,000,000 transactions in 5 seconds, or if I make them do 100,000 transactions in 50 seconds. For me, it does not make. I'm doing still. If I am doing 5,000,000 transactions anyway, so but you say that now you do it in 1 second, then I have to do 5,000,000 transactions per second. But what if my CPU is not fast enough? I'll do 1,000,000 in 5 seconds. So what we're trying to do is, what I thought is that we are reducing the number of transactions and the time both. We are winning both way. Here we are not winning both way.
We are not winning that way. What we are
Understood.
winning is we are winning epochs wise. So let's say initially you would have taken 1,000 epoch to reach the minima. Now you might take, let's say, 700 epochs to reach the minima. So this epoch, if epoch is reduced, then the 300 times this computation of all the things is being saved.
Understood.
Okay,
But-
this
Yeah.
only we can save.
But then going ahead, coming back again, updating, going ahead, coming back, for that's only for W1. Then we have to do for W2. Suppose there are 3 layers or there are 100 layers. Then for W2, we have to do again 1 till whatever X. Then still W99 will also be updated so many times. We will
Yes,
not just stop at W1 and say, okay, W1 is now up to date. Now we can't do a W1 any better. Then we move to W2.
No. We do all of them together.
All
of them.
weights in one flash.
Yes,
W1
all
to
weights in
W99.
one epoch. So you can see here W we are updating, right?
Yes.
So, and
Which is
V
for
is
all the
also
neurons across all the layers of neurons.
all the layers. Yes, all the layers or the weights and biases will update it together.
Oh, all the weights, all the biases of all. There are 100 neurons in 5 layers. 500 biases are getting updated.
Yes, all
And
of them are getting updated.
100 weights. So because weights are same across one layer. Suppose there are 5 neurons in one layer. So 5 weights and 1 weight and 5 biases. So 6 learning parameter per layer. Suppose there are 100 layers, so 600 parameters. for example.
Yes, yes, you can take it.
Understood.
Yeah, all the weights and biases, whatever
In
you want.
one shot, we are updating 500 weights and 100 biases, and again we are coming back. Again, we are updating all the
Yes.
learnable parameters. That's why I think there was a part when Professor there was a question on assignment about number of learnable parameters. So we are updating every learnable parameter in every pass.
Yes.
Oh, oh, wow, wow. That's amazing. That's how because we went into W, that's it opened the Pandora of this part. This week we're getting into W. Last week we had the comfort that you and Professor gave us W and W2W3, we just took it and went ahead. Now
Yes.
we are trying to get W inside W, how we to calculate W ourselves.
Uh, yes.
Yeah.
So now we are, optimizing this part.
Yeah,
Right. VW. So this is
yeah,
what we are optimizing, and
yeah.
we'll still do it next week as well. So that we'll have more of these optimizers, and we'll
Mm,
do it. Uh, and we'll see what happens there, right?
yes.
So just we update all the weights. There's no doubt about it, but it will reduce the epochs. So
Mm.
it might converges better, or it might converges faster. That's what he explains in video. Can you see it reaches faster?
Yes, yes, yes. But
That is the only thing he will always say. Can
yeah,
you see it reaches there faster? So
yes,
faster means we needed less number of epochs. So if
yeah.
the
But
better is optimizer, less
yeah,
number of epochs.
if I say the number of, so if my job, if my compute intensity or my bill or my cost is dependent on number of matrix multiplication or number of computation that happens per epoch.
Hmm.
If the
Hmm.
number of computation per epoch is not reducing, then the
Hmm.
way the number of epochs reduce, but the number of
Hmm.
computation per epoch increases, then
Hmm.
that doesn't serve a purpose. Because that will again, because my systems are built to handle so many computation so many computation. So
Hmm.
while we are, I hope again I'll not belabor the point. My intention here was just to understand the core fundamentals here. If you are
Hmm.
reducing the number of epoch, assumption is that the computation, the number of matrix multiplication, matrix inversion, all those ON square, those
Hmm.
complex time taking stuff, that should also come down because the number of computation per epoch doesn't come down. The epochs come down, then it may not help. It will just, that's the reason people want faster GPU, more powerful GPU, because they want to get results faster at the expense of more computation. My intention is to reduce the number of computation per epoch also while bringing the epoch down.
Uh, so no, that is not possible. But what is possible is you can do something parallelize. Like let's say
Yeah,
this both can happen parallelly, right? That
mm,
that you can do,
yeah,
and
but the
something like that.
computation will
So,
still
but
happen.
yeah, the computation or the number of calculation will not reduce.
Yeah, the number of computes will still be same actually. Okay,
Okay.
and if you are increasing the number of compute per epoch, then that's where the case of moving from a simple CUDA to a A100 GPUs, which is there the Brain Research Center, comes into picture. Because if you are increasing the number of compute per epoch, then a normal GPU or a normal Colab Pro will not support. You need an actual hardcore. Because if we are doing less compute and larger epochs, a simple laptop can also handle that. The moment we
Yeah.
are increasing the number of computation and reducing the epoch, that's where faster and more capable GPUs or CPUs, that's where they come into picture. Understood. I was just trying to figure out the practical application of how we're trying to optimize the number of epochs and in this W optimization.
Okay. Okay.
Understood. Got it.
Okay.
Got it. Sorry. Yeah. Sorry.
Okay. Okay. So okay. Does anybody else have any doubt? Anything related to any which are the topics of, so there are three topics I would say. So one is like annealing the learning rate, which has like three four algorithms on of that, which is very simple. Like you do something so that after some iteration the learning rate will reduce. Another is this two optimizers are given to you. One is momentum based and one other is advanced version of nag nastro based momentum. Okay. uh, I think if it is like pretty understandable, um, then something called stochastic and batch gradient design, or how we do batching and all. So stochastic means we take each point at a time and do the forward pass and backward pass. So full pass we do. Uh, but if it is mini batch, then we take some points and do. And if it is full batch or batch, you can call it batch also. Then you take all of them all of the points and then do the updation. Okay. So these are the 2-3 things which are there in week 4. To summarize you. So any doubts are there?
So post that doubts, I'll ask one question in the week 3, question 7 of the graded assignment. If the answer has just been given, the weight updation post, we have done the whatever eta is equal to 1. I had one small doubt. I'll ask that if I can.
Week 3.
Graded assignment 7, the last one, when we are updating the weights and then we are getting
forward propagate the input through the network. What is the new loss, right? So
yes. My loss was like 0.44, and I had a confusion because the moment I tried to increase the number of, I tried to figure out del W by del L1, that del L by del W1. That's where I was facing a lot of confusion. I was not able to get that value. So if you can explain that part, it will be really kind.
okay.
Yeah.
So so before I explain you, I'll what I'll do is so this practice assignment, right? If you have done this practice assignment, maybe there won't be an issue.
I've done it, sir. I've solved that practice assignment. The
Okay.
updated
So-
loss is the.
So if you can see this, so here what you have to do is W3 transpose, right? Okay. So were you able to find this? Okay, so update all the parameters. So were you able to update all the parameters? W1, W2, what is that? W3. Yeah, W3 and B1, B2, B3 as well. Were you able to do that? Because
Yes.
loss computation is based on that only, right? So you'll do another forward pass and you get it. Nothing new. But for that forward pass, you require this updated all this gradients or updated weights you will require.
Yes, sir. So I was able to do that. Can I share my screen?
Sure.
Just to show where I'm.
Yeah. Go ahead. Let me.
Sure. Just give me 1 second. I'll show the computation that I have done and where I'm getting stuck. Just give me 1 second. I joined from the place where I've done the math and I'll show. Sorry, just give me 30 seconds. I'll loading the Google Meet there. Sir, am I audible?
Yes.
Okay, sure, sir. So I'll share my screen just to show where I'm getting confused. Share screen, continue, start broadcast. So is my screen visible to you?
Yes.
Okay, sir. So so I have computed. So this parameter. So suppose if I need to calculate del L by del B1, for example, and that's where I'm trying to say del L by del A1 and del A1 by del B1. That's the one.
Okay.
and then del A by del A1 is then H1 and H1 by B1. Then if I go next here, B1 prime is B1 minus del L by del B1. So then I'm trying to figure out the loss function, which is here. And
Why? What is B1 prime?
so, for example, if I want to get, so I'll just share, for example, in red. For example, I'll only focus on this red part just to explain the where I was getting stuck. Suppose if I want to guess loss, I need y3, y minus y3 minus. To get y3, I need a3. Because y is dependent on a3, y is equal to whatever g of a3 or something like that. So
Okay.
to get a3, I need a3 is w3 x plus whatever. So to get a3, I need w3, h2 naught, and b3 prime, because these three parameters help me get a3. I already know w3, I already know b3 prime, but I
But what is
don't.
this prime? What is this prime?
So B3
I mean,
B3 prime is the updated weight of B3, because in the previous
okay.
question, they had asked us, I have calculated B2 prime, and they have given us a formula. B2 prime is B2 minus something, and that answer I've got right. I've got full marks for that question. And then there's a question that B2
Okay.
is
Okay.
so
Uh,
if I have B2 prime, then I can calculate B3 prime, because calculating B3 prime from B2 prime is very easy. If I scroll here, so getting B2 prime or B1 prime is very easy, because B2 prime is whatever B2 minus del L by del something, del B2. I've already got B2. I've given that answer. I've got full marks for that. Now if I want to do B3 prime, I can calculate that as well, because I have del L by del B3. It's the easiest part, because del L by del B3 is y minus y hat. Very simple.
okay.
Because that because del L by del B3 is same as del L by del A3.
Okay.
Because if you remember, you had told us that sorry, if I go here, yeah, so if I have to calculate, for example, del L by del B3, it is same as del L by del A3, del A3 by del B3, and
Yes.
A3 is W something plus B3. So del A3 by del B3 is 1. This is same as 1. So this is del L by del B3 is the same as this part. And del L by del A3 is same as y minus y hat.
Wait. Can you explain that del A3 part again? The top part. The topmost red you wrote.
Okay, so sorry, I'll just clear that part.
No,
So
no. Can you just
yeah,
say W minus?
yeah. So yeah, because for example, A transpose X is equal to, suppose W
No, you
transpose.
don't have to write that much. I understood. But if you would have just showed me, I would have. Okay.
Okay,
Can
okay.
you?
Okay,
Yeah.
I'll show that. I was a bit ashamed of my bad writing. So I'll just write just to give an example. So what A3 is for me is I already have H2. A3 is dependent on H2, and W
Blue
transpose, which
three.
is W3 into H2 plus B3. That's a simple
Okay.
formula. And here I know H2 prime, because whatever the H2, it's not H2 prime, it's the same as H2. I already have, if I want to have del L by del A3, for example,
Okay.
into del A3 by del B3, as you told in the last class, this number is always 1, because del A3 by del B3, this will become 0, this will become 1, so this is 1. So
Okay.
if I have to calculate del L by del B3, I can say del L by del A3, del B3 by del B3, and then this is same as del L by del A3.
Yes.
That's what, into 1. That means
Yes.
so now and we know that del L by del A3, we have got the formula is y minus y hat minus, which we have got in
Yes.
the course. So now I have, so the point is I can get del L by del B3. That's very easy for me. The moment I have this, which is whatever y minus y hat, which we already have the value, then I can always calculate del L by del B3. Now the
Okay.
problem is, if I come back here, which is, this is 59, slide 60. Yeah. So here. So now I have, if I have del L by del B3, I can calculate B3 prime, which is easy for me. I have calculated this
Okay.
part. I already
Okay.
know W3. The only
Okay.
unknown which is stopping me from calculating A3 is H2 prime. Unless I know the H2, the updated H2. What is updated H2 prime? H2 prime is H2 is whatever W2 H1 prime plus B2. right? So this is H2 is W2 H1. This is the formula. What I am saying is H2 prime is the new weight calculated by the updated weight of this part. The moment I am updating B2, the value of H2 changes. Let me clear this as well and just write here. So if I do, this is the standard formula of H2, no rocket science. What I'm saying is H2, when I put H2 prime, what changes? The B2 changes. The moment I'm choosing the updated value of B2, I'm calling it as H2. That will help me decide the new value of A3. Because now I have to put the new value of H2. W3 is unchanged, B3 is calculated. To get H2, I need G of A2. To get A2, again I have W2, we have B2 prime, but we don't have H1 prime. To get H1 prime, I need G of A1, and A1 depends on W1, X, and B1 prime. On B1 prime, if I say B1 prime depends on del L by del B1, which again the same formula, del L by del A1 and del A1 by del B1. So the point is, the moment I need to calculate del L by del A1 or del A1 by del B1, del A by del B1 is 1 again. It's very simple.
Okay.
This part
So
becomes 1.
okay, so just so I let you know that I think what mistake you're doing is you are first updating it, then thinking that now since all of this thing internally these things are changed, my del W1 will affected by the previous change.
Okay.
I think I understood that part.
Understood. So
That
because we don't need to update that way. Understood.
so you are thinking that B1 since my B3 is updated, now it will affect my B2 also, or it will affect my H2, so my B2 is affected. But that's not that way.
Oh.
You can consider all of them are independent. All of the weights and biases are independent of changes happening in that epoch. Okay.
Oh.
So you don't consider the updation which has happened now in the updation, like the current updates, right? So whatever updates are happening, let them just store them. Don't use them for any further calculation. You don't have to consider them for this epoch at least. For next epoch, they all of them will be together used.
Understood. Understood. So, would it be possible if you can just show this in a simple way how we would approach it, because I'm getting confused in the level of way I am going through it. Like, how do we? How does that? If you can just explain that collab part, that will be really kind of you, because I went through the code. I just got even more confused how the collab approaches it.
Okay.
Just that collab file, the way the final the questions haven't. That's the only question I got wrong. Everything else was absolutely right.
Okay. So collab part I should explain fine. Give me a minute.
So I'll paste that link to that assignment PDF so that you can grab it. I'll paste it in the chat so that this is the PDF which has the collab. The last file, last page on that PDF has that. I can copy and paste that collab file also if you, but it's there in the last page.
Okay. I kind of get it. Okay. So I've shared my screen.
Yes, sir.
So in this, see first this weights are being initialized. I think so. Okay, from this whatever this numpy file is given to you. And then so we compute first H1, A1, A2, H2, A3, H3. Okay, so this part is clear.
It's pretty simple, pretty self-explanatory.
Pretty
Yes.
simple, right?
Yes.
Now see we want to do gradient descent, right? So what we are doing is W3 grade is NP dot. So we are doing this dot product of this H2 hat and that's what we did, right?
Yeah.
If you
Till
see
question
here,
6, it's clear for me, sir. Till question 6, there's no problem.
okay,
Only
okay,
question 7 is the problem. Everything till
okay.
question.
So where is question 7? Okay, there is no distinction in this,
It's
but I
written, sir.
think
In the green, sir, it's written. Suppose just you scroll just up.
W1.
Yeah. This is the one question Simon starts. I think
This part, right? W1 gradients.
Yes, sir.
So, okay. So see what he is doing is I'll show you. Here, if you see this practice assignment, uh, give me a minute. So can you see this part? Did you understood this part?
Yes, sir.
This is for another practice assignment, but this is related to W2. If you understood this part, same thing we are doing, nothing different. Just the things which are changing is instead of W3 transpose, I think I'll use W2 transpose.
So my problem is always in the first layer, because the first layer becomes really complex. Del L by del W2, I'm able to compute. The first layer, del L by del A1, that's where I want to understand how the weight changes. Because what I got confused was there was a question in question 6, which asked B2 update, which showed how the B2 is updated. We
See,
calculate.
don't look at the code. Okay, don't look at the code. What I'll suggest is don't look at the code. Go through this assignment. Okay, thoroughly. Try to get all the answers.
Yes.
Another thing is solution PDFs given. If you don't understand this hints given, so these are the hints, feedback or something given to you. You don't understand this. Go to this solution PDF. Understand this. Solve this. Okay. If you are able to solve this part, this question, if you are able to solve completely. So in this, they have done for one element, right? 1, 2, 3. So you have to do it for all the elements. Just remember. And I've given the answer for it. That this is the answer. If you are able to do all of this thing, then I don't see any problem. You can't do it. Okay. Don't look at the code, because coding is not natural. Like, I mean, it is for some it is easy, but not for most of it. So just try to understand the math first, because math itself is very confusing in this. So if you are able to do this way, that way, then I think you are resolved. Okay, you can maybe watch last session, or even uh, okay. So I think in last term, the this part, right? So this uh, I only take this session, took the session, so you can watch this as well. So in this, I think I you can watch both, anything. This term also I explained pretty much same, but there I think it went little bit better, the session.
Okay, sir.
Whatever you wish. Okay, you can watch any session.
Yes, sir. Yes, sir.
It is not updated. But fine. So solve this, understand this. But what mistakes you are doing is you are making mistakes. You are updating the weights before it's being used, right? So first you have to use that for loss, right? Now loss loss was never affected by the current updations. Updations happened, but it didn't affected the loss. So how it will affect in the while I am doing back propagation? It should not, right? That is the idea, and that's what we are doing. We are not letting it getting affected. So this part you understood, del L by del A3. That thing is here up to this part. First two things are using that, and then A3 by H2 and H2 by A2 or something like that. No, sorry. Del L by A3 is just this.
Yes,
okay,
sir.
just y hat minus I, and this is using A3 by H2, and then H2 by A2 is this. Same thing you have to do here. Okay, same thing. Like del L by A2, you have to figure it out. A2 by H1 will be W2 transpose, which will come in front. Okay, in front before it. Then this part currently it is del L by A3. So you have to figure out what is del L by A2, which is already given. Like I have given it. Okay, so this thing, if you solve, you will get what is del L by A2. After solving this, that value, the complete value, you have to put as a matrix or vector, whatever you get here, and then go ahead with the solution of this. Fine? Can you?
Yes, understood. Understood.
Do that?
I'll
Yeah.
solve this one again. I'll solve
Yeah,
this one
do
again.
this, and then don't look at the code. Code is, if you can't understand, that's okay. I'm not saying that you should understand this, but understand this part. If you understand this part, then other thing you will understand automatically. Okay. So so I think I'll close the session now. I
Thank you, sir.
I'll come back to B. Okay.
Thank you, sir.
Yeah. If any doubt, post on Discord. I'll respond.
Thank you, sir.
Thank you, sir.
Yeah. Okay. Thank you, everyone. Bye.